People keep asking, if I understand quantum computers? Please, I can barely understand humans. But fine, let's talk about these magical machines that break every rule of logic and still somehow work. Welcome to the world where even your computer doesn't know what it's doing, until you look at it. For decades, computers have followed one simple rule. Every bit is either a 0 or a 1. This binary logic built the digital world, from the first calculators to smartphones, satellites, and artificial intelligence. But a new kind of machine is rising, one that breaks those rules completely. It doesn't think in zeros and ones, it thinks in maybes. These are quantum computers. At first glance, a quantum computer doesn't look magical. It still uses circuits, energy, and data. But beneath the surface, it operates in a world that defies our everyday logic, the strange world of quantum physics. In a normal computer, information is stored in bits. Each bit can be a 0 or a 1, never both. But in a quantum computer, information is stored in quantum bits, or qubits. A qubit can be 0, 1, or any combination of both at the same time. This is called superposition. Imagine flipping a coin. While it's spinning in the air, it's both heads and tails at once. Only when it lands do you see one result. A qubit is like that coin. It exists in a state of probability until it's measured. And with each extra qubit added, the number of possible combinations doubles. That's why a quantum computer with just 300 qubits could, in theory, represent more information than there are atoms in the universe. But superposition is only part of the story. Qubits can also become entangled, a deep quantum connection between particles. When two qubits are entangled, the state of one instantly affects the state of the other, even if they are far apart. Einstein called this spooky action at a distance. For quantum computers, it's not spooky, it's power. Entanglement allows qubits to work together, solving problems collectively instead of one at a time. In classical computers, data is processed in steps. One calculation follows another. Quantum computers, using superposition and entanglement, can explore many possibilities at once. This doesn't mean they're faster at everything, but for certain problems, they are unimaginably faster. Take cryptography, for example. Modern encryption relies on the fact that factoring large numbers is extremely hard for classical computers. A powerful quantum algorithm, known as Shor's algorithm, could do it easily, breaking most of today's internet security. What would take thousands of years on a supercomputer could take minutes on a quantum one. Another example is optimization, finding the best solution among millions of possibilities. Whether it's planning airline routes, designing new drugs, or training artificial intelligence, quantum computers could explore all paths simultaneously and find the best outcome far more efficiently than any classical system. But building such machines is incredibly difficult. Qubits are fragile. They exist only under extreme conditions near absolute zero, shielded from any vibration, heat, or light. The slightest disturbance causes decoherence, the collapse of their quantum state. When that happens, the qubit loses its magic and becomes an ordinary bit again. To control qubits, scientists use technologies like superconducting circuits, trapped ions, or photons of light. Each approach has advantages and challenges. Superconducting qubits, like those used by Google and IBM, are fast but need complex cooling systems. Trapped ions, used by companies like IonQ, are slower but more stable. Photonic qubits use light itself, elegant but hard to scale. The race is on to find which method will dominate the future. Even if we can build reliable qubits, another problem remains: error correction. Quantum systems make mistakes far more often than classical computers. A single logical qubit might require thousands of physical ones to keep it stable. Engineers are developing quantum error correction codes that use groups of qubits to protect information, much like how redundancy works in data storage. Despite all these challenges, progress is real. In 2019, Google announced that its 53-qubit processor, Sycamore, performed a calculation in 200 seconds that would take the world's fastest supercomputer 1,000 years. Critics argued about the meaning of that result, but one thing was clear: quantum computing was no longer science fiction. Governments and tech giants are investing billions. IBM, Google, Microsoft, Amazon, and startups like Rigetti, IonQ, and D-Wave are building quantum processors. China and Europe are also racing ahead. The future of computing and perhaps global power may depend on who masters quantum technology first. Still, quantum computers won't replace classical ones. They are not better for everything. They are tools for specific kinds of problems: optimization, simulation, and cryptography. For everyday tasks like editing video or checking email, your laptop is still better. But in science, chemistry, and artificial intelligence, quantum computers could change everything. Imagine simulating molecules in full quantum detail, discovering new medicines, new materials, even clean energy solutions like better batteries or superconductors. Tasks that are impossible today might become routine. There's also a philosophical side. Quantum computing shows us that reality itself is not digital or deterministic. The universe doesn't compute one outcome at a time. It holds many possibilities in superposition, and only when observed does one become real. Quantum computers mimic that structure. They don't just process data, they process possibility. Some researchers believe that as quantum computers grow, they might even help us understand the nature of consciousness, randomness, and the limits of reality itself. For now, though, they remain fragile, experimental, and expensive. But remember, the first classical computers also filled entire rooms and could only perform basic calculations. Today, we carry far more power in our pockets. Quantum computing may follow the same path from curiosity to revolution. So what happens when these machines mature? Our codes may no longer be secure. Our understanding of chemistry and physics could transform. New forms of AI might emerge, trained on quantum data. And humanity, for the first time, will have machines that think not in certainties, but in probabilities. We are entering a new era. The classical age of computing built our digital world. The quantum age may redefine it, and it all begins with a question as strange as it is simple. What if, instead of zeros and ones, we could compute with everything in between?